Okay, so now we're going to try and cover optimal stopping, but now in infinite time. Okay, so let's just recap a little bit what we were covering on optimal stopping. Okay, so if we go up here, we can remember that a stopping problem is a Markov decision process where you can either stop and you incur some cost kappa x or kx, okay? And there's a cost also for continuing, okay? So there's only two actions, either stop or continue, and you essentially observe some stochastic process, okay? And then at some point you want to optimize and stop in order to incur the least cost possible, okay? And then within that, we came across this rule called the one-step look-ahead rule, which basically said that if we look at either stopping now or continuing one step and then stopping, if it's better to stop now, then we stop at that point, okay? Otherwise, we just keep on going, all right? And this is a very simple kind of myopic rule. It doesn't look too far into the future. It just looks one step ahead at most, okay? And yet we see under some conditions that actually gives an optimal stopping rule, okay? In particular, we said that when a set S, the set given by the one-step look-ahead rule here, the stopping set, is closed, meaning that when you arrive in that set, you're never going to leave again, then this one-step look-ahead rule is optimal, okay? And we did this only for finite time problems, okay? So where there was some bound, okay, on the time at which you had to stop, okay? So maybe there's some fixed time horizon, and within that you have to stop, okay? Now I want to consider the case where you have potentially an infinite time horizon and how this result, okay, that we covered here, okay, that for a finite time stopping problem, the set S given by the one-step look-ahead rule is closed, then one-step look-ahead rule is an optimal policy. I want to extend that and remove this condition about it being finite time, okay? Now, in order to do that, as we know, infinite time problems can be a little bit more tricky, so we have to add a little bit more conditions in order to get this result to work, okay? So, all right, let's go through that then. Okay, so we now give conditions for the one-step look-ahead rule to be optimal for an infinite time stopping problem, okay? And we're going to add two conditions, okay? We're going to assume that the stopping cost given by kappa or capital K, or by k of x, has some uniform bound above, okay? So there's some big K for which it bounds the maximum stopping cost, okay? Further, we're going to assume that there's a minimum, okay, or infimum, to the continuation cost as well. So there's some minimum value C, of which all of the continuation costs are larger, okay? If this is true, then we can argue that the optimal value function for S time horizon problem, okay, so let's say you have to stop within little s units of time, okay, we look at the optimal value function for that. As we let S go to infinity, it approaches the optimal cost for the infinite time problem, okay? All right, so we need to prove that is true, okay? All right. So let's go through that. Just get my notes up. Okay. So here's the answer for that. Okay. So let's take the optimal policy for the infinite time horizon problem, okay? So tell you what, I'm going to zoom in a little bit here so the text is a bit better. Okay, so I'm going to let pi be the optimal policy for the infinite time problem. Okay. What we can see for this okay, is we can kind of compare this to the time horizon problem over S units of time, okay? Specifically, we're going to bound the probability of stopping in S units of time, okay? I'm going to do that as follows, okay? So let pi be the optimal policy for the infinite time problem, and let tau be its stopping time. Okay, so that's the actual time that this optimal policy stops, okay? And note, I'm a little bit cheating in assuming that there is an optimal policy for the infinite time horizon problem. If indeed there isn't, then we could always consider something that's sort of within epsilon of the optimal value for L of x here, okay? So there's always a policy that's within some constant, so, okay, but let's not worry about that too much now, okay? So one thing we can say, let's look in the middle and say, look at the expected value, okay, of this stopping problem. So that would be given by the sum over times up until the time we stop of all the continuation costs, okay, plus the cost that we incur for actually stopping, okay, and now that will be the cost of the optimal policy, okay. Now let's add a little bit of a condition to this. We want to compare it with the policy that stops over S units of time, okay. So we're going to add the condition, okay, that we're going to look at what happens if it stops after S units of time, okay? So one thing we can do now, I'll just add some brackets on this, okay, is we can notice that this, we can apply some bounds to this. So notice the most, okay, that this could give us, okay, is S plus 1 units of time, okay. Okay, so we're guaranteed to have S units in here, okay. So we're going to pick up a cost from continuation of most S plus 1 times capital C, because we've got at least S terms in this sum, and each of these terms is less than capital C, okay? And let's just ignore the stopping cost. We said it's positive, okay? So basically all of this is less than S plus 1 of C, okay? And then what we're going to be left with is the probability of this indicator function, the expectation of this indicator function, okay? So that is definitely less than this because it's less than this is less than this, okay? Now, this is the optimal policy, okay? And so what we can note is the cost from doing this, okay? This must be less than the cost, okay, of just stopping at time 0. Okay, so assuming we start from state x0, then this policy, which is going to be a little bit bigger, less than the optimal cost L of x here because of this indicator function, is going to be less than the cost of stopping at time 0. Okay. Then we've assumed that this is less than capital K. Okay. In other words, what we've done through this bound is given a probability that we have to wait bigger than S units of time, okay, for the optimal policy to stop. So all of this together implies that the probability that we stop with bigger than S steps is less than capital K divided by C S plus 1. Okay, so we've got some sort of bound on the probability that you stop after S steps under the optimal policy. Okay? So in other words, we see this diminishes significantly over time. Okay? Right. And so now we can use this to give us some bounds between L of S and L, where L is the optimal infinite time problem and L of S is the optimal value function over S units of time. Okay? So, well, first thing we can say is L of X must be less than L of S of X. Why is that? Because this gives us the optimal way of stopping, given we can stop at any time, and this gives me the optimal way of stopping, where given I can stop it with some restricted set of times. Okay, so essentially we're minimizing over more stuff here than here, and so the minimum, this L of X must be smaller than this one. Okay, all right, but we could also look at what happens if we followed the optimal policy for S steps and then stopped. Okay, and consider the cost of that. Well, we're going to get at least a cost of L of X for the first S steps, and now assume that we stop at time S. Okay? Well, then the most cost we can get for stopping at time S is K. Okay? But we're only going to stop at time S if we haven't stopped already. Okay? In other words, if this is bigger than this. Okay? So this basically said, this bound basically says follow the optimal policy for S steps. And if the optimal policy needs more than S steps, then we have to stop. Okay? Now that's a policy that works over S steps. And this gives you the optimal value function for stopping over S steps. So this must be smaller. Okay? Now I can use my bound. All right? I see that L of X is now going to be less than, okay, K squared C divided by S plus 1. Oh, and a slight typo, I shouldn't have written an inequality there. Just work that out. It should be a plus sign, sorry. Okay, so now we notice that L of X is less than L of S of X, which is then less than L of X plus something that goes to 0 as S goes to infinity. Okay, so now I can let S go to infinity, and we're going to see that the limit of this guy is bounded between L of X. Okay, so if I let S go to infinity, gives that L of X is equal to the limit as S goes to infinity of L of S of X. Okay? In other words, we've got the result that we wanted here. All right? Okay. So what this implies is whenever this condition holds, okay, that is that there's a maximum to the stopping cost and a minimum to the continuation cost, okay, then the optimal policy over S steps is equal to the optimal policy over, converges to the optimal policy over all steps. Okay, so now we can prove the result that we wanted to prove. Suppose that the one-step look-ahead rule, that the stopping set, okay, S of X, so S, the set of states where the cost of stopping it currently is less than the cost of continuing one step and then stopping. Okay, so suppose that this set, and I should add some comment here, is closed. Okay, so provided this set, given by the one-step look-ahead rule, is closed, then under the condition above, it is an optimal policy if and only if X belongs to S. Okay, so now we can actually use the result that we proved for the finite time problem, and it will imply the result holds for the infinite time problem. Okay, so let's go through that. Okay, just dig out in my notes the appropriate page. Which I can't find, so I'll just prove it. Okay, so answer. Okay. So as before, we have, so as before in our one-step look-ahead rule, so let's get the exercise up. So as we saw in exercise 52, okay, it is not optimal to stop if x doesn't belong to S, okay? Because for the same reason as before, if it's going to cost, if you're going to get a lower loss by taking one more step and then stopping, then you might as well take one more step, okay? So that's certainly true, just as before. Further, from that exercise 52, we have that L of S of x is equal to K of x. Okay, so we showed before that it's if you belong to this set X, and that is 4x belong to the stopping set, okay, then it's optimal to stop now and incur a cost of kx, okay? But from the previous exercise, 55, L of S of x converges to L of x, okay? So L of x is equal to K of x for all x belonging to S. Okay, so it's optimal to stop, okay, and incur this cost, K of x, whenever the state you're in belongs to this set S. All right? In other words, so just to write that down, in other words, it is optimal to stop whenever x belongs to S, and optimal to continue whenever whenever x does not belong to S. Okay? Alright, and that's that. Okay? So next we'll talk a little bit about a specific type of stopping problem, okay? Which doesn't have this one-step look-ahead structure, but has nonetheless a nice structure to it, okay?